Okay, my name is Edwin Peer. I'm a software engineer with Netronome, and I'm going to tell you about extending P4 with C. Sometimes you just have a problem you can't express in P4. Sometimes you want to do something a little bit more advanced than what was contemplated in the language. That's when you want to try and write some custom code that can do that for you. Why is this not good? So what do we want to achieve in this lab? We'd like to do exactly that. We want to add some C processing with custom actions. So they use the primitive action construct in P4 as a hook to call your C at points in the data path, and specifically where we're doing action processing. So in terms of the IDE, the concepts we need to know about is how to add C source files to the project. You're already quite familiar with that, although I believe you guys are sort of kind of swapping who's driving the keyboard. So whoever did it previously, just assist with that as well. And yeah, the idea is we're going to as I said, utilize the P4 primitive actions construct, and that is going to get us an action callback that we can process some C code on. And you'll see that we get past a bunch of things in that C function that gives us access to the headers as they're defined in P4 and the other P4 metadata, so you can access those fields and do various things based on what you see in the packet. This wouldn't be very interesting otherwise. Our examples are obviously very trivial in the lab, and most of them you can do in P4. The final example is a little bit more advanced and actually probably cleaner in C, but and until recently wasn't possible to do in P4, but is now in a later language spec. So it's the kind of thing where if you're ahead of the curve and need to do something special and P4 hasn't caught up yet, you can do it in C. Good. And you're going to do this yourself. So again, we're going to use the same example as I said. So we're actually going to modify that NCAP rule that we had for the previous lab, and we're just going to pop in a filter function there to do something. And then we're going to modify the P4 to call that, and that's as simple as that. And all nice and easy, ship it, profit, IPO. The previous ones were something else. Okay. All right, so as I said already, you have from the callback function, you have access to the extracted headers and packet metadata. You've also got access to all of the C expressiveness on the NFP, the standard libraries that we provide that give you access to all the features of the chip. And you can directly access all of the special memories on the chip and use all the transactional memory features. So that's the subject of the next two labs after this. So we kind of ignore that detail in this lab deliberately. So it's not actually the way you would implement a counter, for example, the way we do it in the lab now, but we'll just sort of gloss over that for now. It's covered in a later lab. Right, so what can you do? You can do everything P4 can do. So sometimes it might be cleaner in C. There's nothing to restrict you. Our P4 is anyway compiled down into C, so if you can do it in P4, you can by definition do it in C. Something nice that you can do is you can do more stateful filtering using the C constructs. You can build yourself interesting data structures and do interesting things with that. Implement new matching algorithms, new filtering algorithms, and you also have access to the packet payload. So I was speaking to someone earlier today who wanted to do really deep packet inspection down to, are there viruses in the payload and that kind of thing. This is the kind of thing you could do in a P4 C construct. So not in P4, which you would require C to do. In terms of what we expect to see, this is now a familiar diagram. We had one group that had difficulty getting packets in on the physical port, and if we have that, there is a bug that we're aware of. If we do hit that again, we'll just switch it over to just moving traffic between the virtual ports. But this is the plan. We're going to send the traffic along the same data path as we did before, using the same example before. So we're still adding the XLAN header and doing all the stuff we were doing before, except now we're going to do some additional filtering and statistics on the packet that we are going to implement in C. Okay, so lab 3. I said we're going to make use of this primitive action construct in P4 to provide the hook for calling our filter function. So from the P4 perspective, this filter func becomes a named action like any other that we can call. And we're just going to plug that into our P4 source. Program Studio in our P4 file. So here's our list of actions we had before. And we can just define our primitive action there like that. Simple as that. Okay. And now we define the link from the P4 side. We need to actually implement this function somewhere. So for that purpose, we're going to create a new C source file. And it's the same, we're still in the debugger. Sorry, this is from the previous one still. So let me quit that. New C source file. And this is the same pattern you've seen before, so immediately save it, give it a name, I'm going to call it filter.c, and then we need to add it to the build, to the project settings. So we insert the C file into the project so that the IDE knows about it, and we tell the compiler to start building from that as the root file. So very much the same pattern you followed with all the other types of files we're dealing with in the P4 project. And if you were to hit build at this stage, you're going to get some errors because we haven't implemented the function itself. So let's take a look at what that implementation will look like. At least to do a simple, again, we're going to just drop the packets. So it's not very interesting, but it's a good example. So I'm a bit ahead of the, so here we are. So this is the format of these functions. Why can't I cut and paste from here? There we go. So whenever you want to do P4C in our implementation, you include this header PIF plugin. So we're actually implementing a plugin in the terminology we're using here. And in that plugin, that header, it includes all sorts of interesting structs and data structures based on your P4 definition of your parser. So if you had Ethernet headers, you're going to have something in that data structure representing your Ethernet headers that you can access, you can write to, you can read from, and you can do all these kind of cool things. So that's what you get passed here. You get in this headers pointer is a pointer to a data structure that contains exactly that, along with P4 metadata. And the match data contains the parameters that were passed to the instance of the action that was matched or that was executed for your packet. So if you passed in a port, for example, you'd be able to access it there from that. Like the forward action had a destination port that we passed it, this would be the same thing there. You'd be able to access that parameter there in your C function. And then you're expected to return something that determines the fate of the packet. So if you return this constant, this PIF plugin return drop, then it's going to drop the packet every time this function gets called on the packet. Just in terms of the function name itself, the pattern that's followed here is it's always PIF plugin, followed by the name of your primitive action that you defined in your P4. So if I had called my primitive action something else, if I had called it drop func, for example, which is what it's currently doing, but I called it filter to be a bit more general because we're going to do other things with it, then it would be PIF plugin drop func. Okay, so it won't build, and if you go and write the C code before you build the IR from the P4, you're going to get an error because the headers don't exist yet. So, but you should all have that because you did the previous lab, so that they should all be done there. We're not changing the structure of that. So that's great. We can now build our circular file. For those of you who don't know what a circular file is, it's a round bin that you can file things in. And so I'm saving that after changing it. Just want to make sure I'm not getting ahead of the instructions here again. Oh, we actually need to define where this function gets called in our action pipeline. So I'm just going to add to our in-cap action that we already have. Let's call the filter function that we've just defined, or the filter action, if you're talking in P4 parlance now. So our in-cap action, before we do anything else, we call our filter. And now we're going to always hit that first. Some of you noticed during the previous labs that you can't actually single-step code execution inside the P4 language. But what you'll notice if you look at the C function as we run through it, is you can actually single-step through that and do all sorts of other nice debuggy things like add watches for variables and things like that. I'll get to examples of that now. Okay, so let's build it. And hopefully we've done it right. We're going to, just tell me something's out of date. Do I want to build it? Yes, please build it. Okay, so everybody sort of up to date here. Are there any questions while we wait for the build? Okay, that's a good sign. No errors, no warnings. That's what we want to see. Should be hard to have errors if I cut and pasted the code. Okay, there we are. It's now running, or not yet running. It's loaded. Next step is to click run on the project to make it actually start executing on the NFP. And I'm interested in looking at the counters to see if what I expected to happen happens. So I'm going to just open up the system counters here in this display. Oh, so hold on a second. Sorry. Okay. All right, so now we're going to feed it a packet again. So let's find our terminal. It's the same pattern as before. Going to send. You'll see there's a number of PCAP files in root's home directory on the server. I'm deliberately using this one because of the next thing we're going to do. So you can switch to using this one too. UDP 10.0.0.100.pcap. It's going to send a UDP packet to that destination IP. And what I expect to happen if I send it and refresh the counters is I've received it and I've dropped it. Where am I playing it back here? Looks like we're getting all those IPv6 packets again. All right, so what I'm going to do because of that, and just if you battle with the, so an issue we've had on some of the machines is there is a minor bug in the loader, and what is happening is the Intel NIC in the server is sending IPv6 discovery packets even though we've turned off IPv6. And those packets are coming up while the chip is in a state of half-loaded the firmware. It's loaded it, but it hasn't started it, and that's causing issues for us. So what I'm going to do is I'm going to change my rule definition on the NCAP table. And if you don't get troubles, don't worry about this. But if you most of you didn't hit this problem, I'm going to just match on V0 and go out on V1. And that's all I need for my lab. So we're going to build this to update the rules. And now instead of playing the packets dump them there. Play them here instead. Okay, so we'll see what I've done there. Basically, I've inverted the data path just like that, or changed the data path. It's now forwarding from one VM on the host to another VM on the host instead of from a physical port to something on the host, for example. Sorry? Yeah, you might be in the same issue again. Okay, so now what I expect to see is refresh the counters. Okay, so let's see what happens when we send a packet in. Wrong terminal, this terminal, there we go. And VF0. And presto, there we have what we want. We see a packet that got dropped by our drop rule in the counters there. So one other thing we can possibly do to just get better visibility into what's happening there is it might be interesting to just set a breakpoint. Oh gosh. Filter, where are you? Okay. All right, well, that worked. Let's go and have a look at our C code. So now let's put back in the accept action. So I'm pretty sure that's just a matter of return forward instead of return drop. So we change our C code to return forward. Save, build. And what we should have here is our wire again. So okay, so now if we send it packets, we expect them to actually come out the other side. So let's see if that works. So we dump on the other interface and we send the packet in here. And presto, there it forwarded our packet. We can look at our counters again. Oops, I've now pressed something I shouldn't have. And refresh our counters. And we see it's no longer dropping those packets. Excellent. Okay. So this is not a very interesting filter function yet. So let's do something more interesting. Let's implement some policy here. So actually, we are doing more enhanced matching. We're doing matching inside our action in a sense, because we're calling this filter function, and we can actually implement policy there too. We don't have to only implement actions. So let's do that. Before I can do that, I need to match on something to do policy, of course. So one of the things we're going to do is we're going to implement some kind of matching logic on the IPv4 headers of the packet. So we need to actually define the parser stuff for that in P4. So again, it's defining a header type that matches what the IPv4 header looks like in the packet. So let's go do that in our P4 implementation. So I like to put it with the rest of the parser definition. So we parse Ethernet, and then we parse the parser definition. Oh, no, sorry, not there. It's actually the parser there. Let's define the IP type here. Let's define IP here. That's nice and neat. And then I mustn't go off script. You see, I must follow the script. Then we need to instantiate it somewhere. So same as you did for the XLAN, instantiate the header. And then we need to tell our parser how to get there. So we can definitely have an IPv4 packet inside an Ethernet header. We expect that. So let's add the select for IPv4 inside our Ethernet header. So if our ether type is IPv4, then go parse an IPv4 header. And for completeness, we'll update the XLAN description as well, so that if we have an IPv4 packet inside an XLAN header, I'm not sure if our example actually does that, but that's fine. It's not too important. For completeness, we'll just do that. I think I actually cut the whole thing. No, I didn't. I just cut this part. Okay, so that then should parse XLAN, and then if it is an IPv4 packet inside, go parse IPv4. Otherwise, just return it. And then we actually need to go and build the parse node itself for IPv4. So just by doing that, now we expect to have a P4 parser that understands IPv4, just like that. Actually, this one bit here about a parser. Yes, the XLAN parser. Let's add the extract IPv4 there. Okay, so now our P4 should understand IPv4. So let's build the P4 representation again. So stop the debugger. The intermediate language. Ah, gosh, what did I press? I'm going to rebuild now because I'm not sure what I pressed there with this touchpad. Sorry, it takes a little bit longer, but I just want to be sure that I've built everything. I might have cleaned the build there now. And we'll see we've got a much more interesting looking parse graph happening as a result. So now we parse the Ethernet header. If it's XLAN, we parse the XLAN header, then the IPv4 if there's IPv4, and otherwise we have IPv4 inside just an Ethernet header, and we sort it. So that's kind of cool. You can see what's going on. And And you're going to see this build's not going to fail because I already started updating the plugin function earlier, and I removed the return statement there. So that's why we're getting missing return statement warnings. So it actually did build, but it's not going to have predictable runtime results if we actually run it like this. So let's fix that. So we'd like to, in our filter function now, the logic I'm going to implement here is going to match on a specific IP. Well, first we're going to look if IP headers are even present. If they are not present, we're going to just drop the packet. So if we send a non-IP packet, we expect it to be dropped. And then we're going to get a reference to the IPv4 header. So there's a utility function generated by the P4 compiler code generator that will now provide, because we defined the IPv4 parser in P4, we now have a way to get that header out, pointed to a struct that represents that header. And then we're going to go match on a field inside there. So we're going to, if the destination is 10.00.100, you can see I've just done a cheap and nasty match on the 32-bit IP number there. I haven't done a parser for the string value of an IP. So this is representing the IP address 10.0.0.100. And if the packet is destined for that address, then drop it. Otherwise, return forward again. So we forward everything except the packet we want to drop. So obviously, this is a bad example of something you would do in C, because this kind of thing can be expressed much better in P4. But for the purposes of illustration, let's do it. Sounds like fun. So I'm just going to replace my implementation. Copy that. Put it here. Paste it. Lose some of the spacing, which just makes it look a bit untidy, but that's fine. Right, save it. Let's build it. Let's run it. Any questions at this point? We've got another wait for the build to happen, so if there are any, we can try and answer them. Cool. This time no errors. Is the pace good? Is everybody keeping up? Sorry? Oh, that's all right. That's okay. Oh, I should have actually typed it all out. I think I should have done that. I did that in the dry run. It worked quite well. But otherwise, I spend a lot of time up here waiting for builds, and yeah, it's a good idea. I'll type the next one. Okay, well there we have it. Let's run it and see if it does what we expect. So again, I'm going to be dumping on the destination. I'm going to send the packet I expect to drop. This is the destination that we're dropping for. And unless it, didn't forward it, because that's what we asked it in the policy. So if you recall, our filter said if the destination is this, return drop. So that's exactly what happened. Now I've got another UDP packet in a PCAP that has got a different address. Send that one, and we would have expected it to come out the other side. Did we receive it? I think we did. we dropped that one, but expected it, yeah. If I send this one, I expect it to not drop. Did I start this again? So what I expected to see. Let's just see if we can match on. So let's look here. Breakpoint here. See if things are happening as we expect. Okay, so I sent the packet in, we hit our breakpoint in the filter. Let's just step through this. Here's an IPv4 packet. Good. And we return forward. Why, oh why don't you forward? Oh, I know why. The packet is coming out VF0 because my rule table is probably not correct. So look. In cap. Yes, my rule forwarding is going to be F1. That's what I want. Let's just do V1. Match V0, which was matching fine. Board. Oh, I didn't. Sorry, I rebuilt, but I didn't start the debugger. Right, let's run it, see if our luck has changed a bit. If not, we'll just move on as if it worked, because the next step doesn't depend on actually sending the packets out. Packet in. Now we hit our breakpoint again. Let's remove the breakpoint. So you know the demo's live. And there we go. There's our packet matching. All right, so I think my format in the rules, there was a problem with that. So if I send the packet destined for 0.100, it gets dropped. If I send the packet destined for someone else, it gets accepted. So that policy is now being implemented in our C filter function. So we've abused the action a little bit to actually do some matching. It's kind of cool. These are the things you can do when you have the expressive power of C at your disposal. Okay, so let's do something a little bit more interesting. This is something that when we conceived the example, it was something that wasn't possible to do in P4. It's very difficult to come up with realistic examples that are simple. The moment you want to try to do something fun, it very quickly gets too complicated to do in a short lab. So what we are going to do is we're going to maintain a histogram of statistics for various IP protocols, and we're going to index that in an array based on the actual protocol ID we see in the packet. So that's so previously in P4 you'd literally have to define a rule for each thing you're trying to match and then increment a counter for each one, which would have been very clumsy in P4, but apparently now they can do this kind of thing too. So it sounded like a nice idea. So we need to declare our array of counters. And instead of dropping these packets now, I'm going to actually go and increment that counter. So counters at IPv4 proto. David, you said you actually think it's IPv6 the moment I said IPv4, you know. Yeah, I'm disturbing that is up here. I'm like, what? I just typed IPv4. Right, okay. There we are. Proto counters, did I do it right? On IPv4 proto. So there I typed it to do it at the same pace you have to do it. And let's build it again. Yes?
What happens with this counter? Are they shared between the various engines?
Yes, they are shared.
How expensive is to drop data?
Okay, so Gavin's talk, or I don't know if Gavin's going to be, is Chris going to be presenting it now, is going to, the next labs are going to cover memory placement and sharing data structures in memory and that kind of thing. So I was wondering if somebody was going to ask about this shared here. So that is the C construct, the annotation that is causing this data structure to be shared amongst the threads. And so they all update the same thing. Now this example is actually not worrying about atomic updates and all these kind of things and doing it in a way that is transactionally safe. But this is the net effect. We're having this thing declared in some shared memory local to the threads, and then we can access that directly. So lab 4 and 5 will get into more detail on exactly answering your question. Okay. So the break after this.
Yes.
Okay.
If you're done, we do
Yeah.
reconvene at 2.
Fine. Okay, there it's loaded. Let's run it. Okay, so in fact, let's not run it because the problem is now we've got this histogram, but we've got no way to read it. So let's use the tools to set a data watch on that histogram so we can actually see the counters increment. So in our filter.c, if we open it up in the thread view, the detailed instructions step by step are in there. You double click on the thread and you select the filter.c, and that's all detailed in the instructions you've got. We want to add this to a data watch. So it's a right click on the thing we're interested in. We say set data watch for proto counters. And then we can ignore this warning and ignore all of the ones that you're going to get. And turn on the data watch pane. And there you can see our proto counters variable, the array defined. So let's send some packets. So there's a bunch of sample packets in the root directory again, root's home directory. So there's a UDP packet that we've been using, and now we're only counting for packets destined for that host. So let's send to 100 again. So there's 1, 2, 3 UDP packets. Let's maybe send an ICMP packet, and we expect there might be some TCP traffic happening. I don't know how many I did now. Oh, right, we should have been running, but that's okay. We expect them all to be forwarded now. So did I run my dump? I didn't. So let's just send another packet and make sure that it's forwarding. Yeah, we're still forwarding now. And we expect to be able to see now, if we stop the micro engines, there's our ICMP packet counted, there's our 6 TCP packets counted, and our 3 UDP packets counted. And that concludes the realistic part of the lab.